Okay, wonderful. We got Monday, the 20th of July. We're starting the 5th week. In other words, we have completed 4 weeks. We're halfway through our summer session. All right, let's talk about midterm 2. Midterm 2 will cover chapters 8, 9, and 10. Okay, let's talk about chapter 9. We're going to exclude section, and I should put a dot here. That's an abbreviation for section. We're excluding section 9.10. We're covering part of chapter 10 up to page 380. All right. And by the end of today's lecture, we will have achieved page 380. So that's where we're going. And furthermore, you know, for the current homework assignment, which is part 1 of homework number 7, this is precisely what you need for one of the problems. All the other problems can be done without chapter 10 material. One of the problems requires chapter 10 material, and precisely this page 380. Okay, now of course that's going to be Friday of next week. Another way to say that, July 31st. Okay, so now we do have a midterm 2 folder I created earlier today, and this information is codified in that folder. And I will be adding some more information, etc. All the bells and whistles will have all kinds of materials in there for midterm number 2. Okay, let's talk about the homework. So as I mentioned, homework 7 part 1 is due tomorrow. Later today, I'm going to post part 2 of homework 7. So let's write that down. Okay, I will post it later today. It's going to be due Friday. All right, so far so good. Yeah, my office hours this week. All right, here's what we have Monday, Tuesday, Thursday, Friday. Okay, 8 p.m. Tuesday, 11 a.m. Thursday, 8 p.m. Friday, once again, in the morning, bright and early, 11 a.m. Okay, so those are the office hours. You can see the intention here is to have the office hours correspond to the homework. However, not immediately before the homework due date end time. That ends up being not so useful. Reading assignment. We're going up to page 407. Okay, so that's by the end of the week. Okay. Yeah, so those are the announcements. Lots of, you see it's a very active and lively situation here in Physics 105. Never a dull moment, really. And let's get right to work. We have to wrap up our discussion of the Foucault pendulum. Okay, you remember the Foucault pendulum. And this is a nice opportunity to remind ourselves about some really crucial three-dimensional geometry that is relevant for the first part. Remember, homework 7 has 2 parts. The first part is due tomorrow, and we're doing some important work in a 3-dimensional space because that's going to be important throughout the course. So 3-dimensional geometry. Let's take a second to remind ourselves okay? And on the 16th, okay, Thursday, this was on our chalkboard, so to speak. Nice picture here, the Foucault pendulum with extra color for clarity. And what we did is we looked at the case of small angles. So beta, if beta is small, so the pendulum is near the equilibrium. We're not considering drastic excursions away from the equilibrium. This allows us to do a theoretical analysis. Of course, part of the new philosophy of the upper division courses is you have computers available. You could look at the behavior of the system for large values of beta. You can do that on a computer pretty much just as easily as small values because the equations of motion are available to us. We could write it out. So that'd be interesting to do a detailed examination of the behavior for large beta and look at some of the central results. For example, we're going to predict the precession, right? The plane of the pendulum. The pendulum appears to be swinging in a plane to someone. Remember, we've talked about different time scales. Some problems have 2 time scales, and this is an example. The fast motion is the oscillation of the pendulum. Okay, that's on the scale of seconds. The slower time scale is the precession. That's on the scale of once per day. Remember, order of magnitude once per day. It's going to depend on your latitude. So it'd be interesting to put this on a computer, do high precision work, and see if you can predict excursions away from this precession frequency that we are deriving under the assumption of low amplitude, so small oscillations, small beta. Okay, so what we did, under the assumption of small oscillations, you see this nice rectangular box here with 2 differential equations. We arrived at this system of 2 coupled differential equations. All right, it's very nice. Of course, if capital omega is 0, they decouple. There's another special case. If the cosine of theta is 0, they decouple. So if you're on the equator, that's going to be a little disappointing. The cosine of theta is 0. My guess is equatorial regions, they don't think Foucault pendulums are so great because they don't work. They don't do anything. Yeah, that's life on the equator. You got a pretty boring Foucault pendulum. But anywhere else, I hate to have to phrase, I don't mean that in a bad sense, but that's the physics of it here, folks. If you're near the equator, you've got a very small effect. Would be fun to try and measure it. Okay, so again, the structure of the equations. And notice this plus sign and this minus sign, okay, this quintessential kind of trademark of many of these problems ultimately coming from a cross product. Remember what we talked about? We talked about the surface of the earth. We looked at the Coriolis force. We talked about different ways to describe the Coriolis force, deflections to the left and the right, things like that. Those are the words we used. All of that coming from the cross product. And here, in this particular problem, we have a plus sign for this one and a minus sign for that one. That structure originated from a cross product. Now, what's very interesting is we can introduce this complex. This is a lowercase eta. It looks like a lowercase n, but it's a lowercase eta. We introduce this complex variable. Notice it's a construction. You take these 2 functions, x and y, of course, they're real functions. Those are the coordinates of our pendulum bob. And you construct this complex quantity. This construction, the structure here with a plus and a minus sign, is now wrapped up very neatly in this complex multiplication. You know, when you multiply complex numbers, the resulting complex number has a magnitude that's equal to the product of the magnitudes. It has a phase angle relative to the plus x-axis. That's the sum of the 2 phase angles. So multiplication by the imaginary unit is a 90-degree rotation. This is precisely the structure we have here with the 90-degree rotation. So yeah, there's a very nice harmony here between this 90-degree rotation. Essentially, those are the remarks we made about the Coriolis force, right? You have this deflection, depending on if you're in the northern or southern hemisphere, and it's perpendicular to your velocity vector. So the Coriolis force causing this kind of deflection. Here, that's encapsulated nicely with this multiplication by the imaginary unit. You know, something wonderful happens here, and this again is something we should talk about looking ahead to the second midterm. we have arrived at a differential equation which has the structure that we studied in chapter 5. So once again, chapter 5 is a chapter that contains some foundation material that will serve us well throughout the course. And let's return to what we were saying earlier today. We got a midterm. It's sneaking up on us once again, but we've got a midterm. The midterm covers this material. Furthermore, you will need material from earlier chapters, such as chapter 5, if you see it mentioned amongst this material. So that foundation material belongs to our core set of skills, and it's understood that you need that stuff. And so it is in that spirit that we describe the midterm with this description. It's understood that you'll be utilizing core skills from earlier in the course. All right, cool. So this is precisely the structure we had earlier in the course. Notice it's a second order differential equation. We have second order time differentiation here, first order time differentiation here. So it's a second order. That's the convention, right? If you say second order differential equation, derivatives exist up to second order. The coefficients are constants, right? This one happens to be, involve the imaginary unit. It's a complex number, etc. So again, the techniques that we learned in chapter 5 can be utilized to solve this. Let's take a second to discuss this, and then we must move on. Chapter 10 is calling to us. We must not ignore the calling of chapter 10. So here we are with our notes. We know from experience, this kind of an equation can be solved using an exponential ansatz. Remember ansatz? This is an educated guess. We're going to look for solutions. And I'll follow the notation in the book. Notice it's a little bit dangerous notation. We're going to say the following. So you see the problem here, right? X and Y are coordinates. They're measured in meters. Okay. Now, how could we do this? We wrote down an equation. We know e raised to any power is a dimensionless number. And furthermore, you must raise it to a dimensionless power. Well, we succeeded there. This is dimensionless because alpha has dimensions of inverse time and t has dimensions of time. So everything's okay there. So properly speaking, you would put an amplitude out front. Okay, but observe, this is homogeneous, right? Every term has eta to the first power. So any sort of multiplicative constant here would immediately drop out. All right, so it is in that sense that this ansatz is written in the book. And it's important that we talk about these things to really have nice, crystal clear discussion. Okay, so it's the familiar story. You plug in the ansatz, you get a quadratic equation. So I'll write that arrow there for logical implication. Quadratic equation, might as well write out the equation, right? It's alpha squared. And then furthermore, let's just clean up. Here's a rigid object. Later today, we're going to talk about rigid objects. Okay. Alpha squared. Okay. Now we got the minus 2 omega z alpha minus omega naught squared. Okay. Notice what happened here. We have a quadratic equation, right? This is now purely algebra. It's algebra, it's a quadratic equation. The original problem was, it's a much more difficult class of math problems. This is a differential equation, considered to be very difficult class of problems. We've reduced it to a quadratic equation, which is considered, trivial. And furthermore, it's a quadratic equation with real coefficients. That was the remarkable insight. We put the imaginary unit here. We actually put a minus sign because in physics, we often have our phase factors that involve time, we have them with a minus sign. We often write e to the minus I alpha t. In electrical engineering, they like to use the plus sign. So just so you know, when you, for example, when you take physics 111A, you're looking at the world of electrical engineering. They'll do it with the plus sign here. Again, it's an arbitrary convention. And the fact that we chose to put the imaginary unit here in front of the alpha is completely equivalent to having chosen a different symbol here without the imaginary unit. This has the nice effect of making all the coefficients real. If we had not put the imaginary unit there, we would have an imaginary unit here, okay? The level of effort is the same, but this is nice to be in familiar territory. It's a quadratic equation with real coefficients. Okay, we can solve this with ease. Here we go. We got the omega z. Remember, that's the z component of the angular velocity, right? And again, that's the coordinate system you need here for our, quote, Stonehenge problem. It's really Evans Hall. Okay, and we got the plus or minus. Okay. All right. Now, again, one of our core skills, series expansions. And looking at something like this, again, here are the two different frequencies. Remember, we've talked about the fact that there's a whole world of studies out there where they look at problems with multiple timescales. And a nice example would be molecular physics. You've got vibrational timescales and rotational timescales. Those are different timescales. Also fascinating things going on in solar system dynamics. Really cool stuff with different timescales. You may have Saturn's rings doing one thing. You may have precession on a much different timescale. Okay, so here we have two different frequencies. Omega naught has dimensions of inverse seconds. Omega z has dimensions of inverse seconds. Omega z would more naturally be expressed in inverse days, right? Because ultimately it's 2 pi over the, the omega itself, the capital omega, is 2 pi over 1 solar day, right? So, yep, so here we go. Well, actually, you have to think about it. It's a solar day or sidereal. That's a separate issue, but the point right now is we're interested in the timescales. So high frequency and low frequency. And so for what we're doing, we're going to do this approximation. Okay. Right. And of course, we could carry more terms, right? This symbol indicates we've made an approximation. The structure is omega naught is very large compared to omega z. And here there's squared, omega naught squared. So this truly towers over omega z squared. So we've, to a very good approximation, this squared is equal to omega naught. All right, so we have these two solutions with a plus and minus omega naught. Okay, so the general solution, right, this belongs to our core skills. And we like to write it in different ways. Here, let's look at it in this form. You know, there are equivalent ways to write this general solution. And from time to time, we may choose one or the other. Okay, so this is very illuminating. Again, the structure with the plus and minus sign, we have these two solutions to the quadratic equation. And notice omega naught is much greater in magnitude than this omega z, all right? So both of these solutions, because of the minus sign here, we have a common multiplicative factor, this e to the minus I, and let's make sure that's visible. There we go. That's a shared multiplicative factor. We're using this property of the exponential function that if you got a couple terms up there added up in the exponent, you've got a product here. So we factored out a common multiplicative factor. And this structure that's inside of the square brackets now is a familiar structure to us, right? You could equivalently write this out with sines and cosines. Okay, so a nice example. Let's go through how you would actually use this for a typical example. And in the laboratory, you would prepare an experiment with some initial conditions. So let's be very clear. That's the initial position. Okay. And let's be creative here. Choose some capital A for amplitude. Everything else we're going to zero out. Okay, so yeah, you have the freedom to be creative. Perhaps we're not being too creative here with a bunch of zeros, but nevertheless, the point is, you as the experimentalist, you choose the initial conditions. Okay, you run the numbers, so to speak. You plug in and enforce these initial conditions. This is a nice case where we have C1. We got the A upon 2. All right. And so the picture that emerges here can be conveyed very clearly with this nice formula. So the complex eta as a function of t, again, that's both the real and imaginary, both the x and y coordinates expressed here as the real and imaginary parts of this eta. We got the amplitude, the slow time scale. And again, it's the z component of the angular velocity vector, the omega z. Okay, times t. And here it's a cosine, omega naught t. So the two timescales here, they both appear. The solution is manifestly the product of two functions. One function depends on the fast frequency. Here's the fast frequency. The other factor, this factor here, the slow frequency. All right. So here it's very clear. We have a precession, and this capital omega z, that's the angular velocity of the precession, right? Because the cosine, that's the familiar oscillation of the pendulum. This is the swinging of the pendulum with frequency omega naught. And this serves this exponential factor e to the minus I omega zt. That's a phase factor. So in the complex plane, that very slowly, let's draw the picture like so. Okay. And so as a complex number, this thing is unimodular. It lives on the unit circle. Let's bring in some nice colorful ink here. Right, this is a unimodular complex number. Regardless of the value of t, this is somewhere on the unit circle. Okay, so I've drawn the unit circle in the complex, I should say this is the complex plane. So for that red ink, okay, so in red ink, I've drawn real and imaginary. This is the customary way to label the axes in the complex plane. This precesses clockwise. Remember, if it were plus, which it is not, but if it were plus, we would be going counterclockwise. That's the usual convention for phase angles in the complex plane. But there's a minus sign here. So we're going clockwise in the complex plane. And then the x and y values shown here in black ink, those are the real and imaginary parts. Okay, so the motion here is it oscillates back and forth very quickly, and then that slowly rotates. So that's what I'm doing, slowly rotates clockwise. Notice the tip of the pen is going back and forth, and then I'm slowly rotating that clockwise. Now it's parallel to the x-axis. And look at that, we got a nice animation. Now it's going parallel to the y-axis again. So there you have it, the Foucault pendulum, and a wonderful opportunity to review our skills with this coordinate system, which is a very important coordinate system to us. Okay, now let's return to the big picture. We're going into chapter 10. Okay, we're going into chapter 10. Lots of fascinating stuff. For example, the motion of the free rigid body. And we will be doing some careful analysis of videos done in a wonderful microgravitational environment. And I'm referring to the International Space Station. So if you're an astronaut on the International Space Station, the phrase that is used is microgravity. To a good approximation, you can say you're weightless, pretty much zero gravity. And you can do some really cool experiments like have an object just tumbling in front of you. For example, here's a rigid object. If you're on the space station and you got some spare time, you could just throw this into the air and it would start turning about a certain axis at any instant in time. Here on Earth, it would fall to the ground. So we can briefly do these experiments. We can throw something in the air, observe its rotational motion briefly, but then it hits the ground. And often that's just much too fast before you even get a chance to really think about what it's doing. It struck the surface of the laboratory, the ground floor, and party's over. So yeah, the motion of a free rigid body is surprisingly complicated, truly complicated. In fact, some of the results cannot be expressed using elementary functions, right? You have to invoke certain special functions from classical mathematics. So the rotation of a free rigid body, truly remarkable and contains some surprises. We're going to see some surprising behavior. So with that in mind, let's begin chapter 10. Okay, so first we're going to talk about a collection of particles. These particles do not have to belong to a free rigid body. They could be, perhaps we could have a diamond crystal, okay? That would be a nice example of a rigid object. But for this collection of particles, we're not making any assumptions about the rigidity. It could be arbitrary. You could be doing astrophysics and you have some large cloud of dust particles, right? There's a whole bunch of that stuff out there. And the notation will be the familiar. Let's write out, for example, capital R, the center of mass. Okay, so some of the notation here is very, very important to us. You remember earlier in the course, we had this index alpha. This is the particle label. So if you have a collection of particles, remember it's understood okay, this index, the particle label index alpha, right, lowercase alpha, it ranges from 1 up to capital N. So capital N is the number of particles. They're distinguishable, right? We're doing classical physics. We could have written the more detailed version of this formula. You would say alpha equals 1 up to capital N. That means you could have explicitly written the limits of the summation. It goes from 1 to capital N in integer steps, stepping by 1, okay? But often it's just understood that the range of the index is from 1 to capital N, and so often we write it in this form. It's just understood you're summing over all allowed values, and that means from 1 to capital N. The lowercase m, that's the mass of particle alpha. And then r sub alpha, this is the position of the particle. So you remember good old equation 734, very important to us when we were doing Lagrangian mechanics. Same notation there, so we love this notation. This capital R is the center of mass. Okay. Yep, capital R, that's a well-known result. You know this result from your first year physics course. We like to use capital M for the total mass. Okay, so these are examples where we're summing over the particles. Okay, and so let's continue in that spirit. The total momentum, and I like to emphasize this is a capital P. I write it with this serif feature down here at the bottom. Again, we're summing, I almost wrote, might as well write it clearly once. Alpha going from 1 to capital N. That's what we're talking about here. Okay, and that's going to be the mass of the particle, the velocity. Okay, and now notice the notation. We've got the lowercase r with the arrow over it. That means we have a vector. That's a position in space. The alpha is a subscript, right? It's the particle label index. And the dot indicates time differentiation. So what we have here is a lowercase r with 3 pieces of decoration, the alpha, the arrow, and the dot. Later today, we're going to have a lowercase r with 5 pieces of decoration. It's a truly monstrous constellation of symbols here. We're going to have a lowercase r with alpha, an arrow, a dot, and a couple other things. It's going to be truly amazing. So yeah, that just goes to show you how cool this stuff is, the notation. So this we recognize as the familiar non-relativistic momentum of the particle. Okay, so with that in mind, we're going to need some notation here, crucial notation. All right, so this is notation. We're going to define a symbol, the position of a particle relative to the center of mass. Okay, so position relative to okay, and let's draw a picture to go along with this. I like to I like to draw these axes just to capture an image of a 3-dimensional space. Okay, so there's some origin. Might as well put it here. And now you have these particles, just for concreteness, let's say you have a large cloud of particles. Okay. Maybe you're doing astrophysics and you've discovered some truly amazing cloud of particles out there. Okay, so this is intended to be a big blob with a huge number of particles. All right, you've determined the center of mass is here. And we like to put a capital C, capital M for center of mass. All right, now using our notation, right, the capital R is the position vector of the center of mass. So that goes like here in this picture, like so. Okay, so you see there's the center of mass, the capital R vector, like so. Here's a typical particle. Obviously, there are huge numbers of particles. Here's a typical particle, the mass m sub alpha. And so that's a way of depicting that particle. Okay, you know, that vector from the origin to this particular particle, this is notation we have already introduced, right? It's certainly present up here. We have the lowercase r with the alpha and the arrow. Okay, so that's our position vector for this particle. And now the new piece of notation that we're going to introduce here, positions relative to the center of mass. So I think this calls for some truly remarkable it is this thing here which we must talk about. It is this red arrow which we must talk about. This is the relative position, the position of that little particle relative to the center of mass. Okay, the notation r sub alpha, because once again it's that particle alpha, that's the name of the particle. And now we put the prime. Okay, so let's be clear. We've seen this many times over. Sometimes prime denotes differentiation, especially if you have a function of a single variable. That's not the time you typically use the prime. Oftentimes, the prime is not differentiation. This is an example where it is not differentiation. Once again, it's a means of producing a symbol that has a similar appearance to an existing symbol, but has some sort of important difference. And the important difference here is capital R. That is the difference. And so let's write out this formula. R sub alpha equals capital R plus the R alpha prime. Okay, so you see what's happening here. It's useful to write this as a vector sum. Vector sums are nice because you can do the head to tail construction, right? If you have a vector sum, that immediately tells you about a head to tail construction, and you can see that here. We start at the origin. Here's this capital R vector going to the center of mass. In a vector addition, you see the head to tail construction. We have the capital R vector, then we place that lowercase r sub alpha prime. That's the red vector. It's a head to tail construction because that's a vector sum. The resulting object, you get to this point here. So the result is a vector that starts at the origin and goes directly over there. That's the familiar r sub alpha vector. Okay, so in this form, it's a head to tail construction. If you like, you could do a vector subtraction. We can easily solve this. R sub alpha prime is, all right, you subtract the capital R from both sides. Okay, so that has the structure of a vector difference. It's the vector difference between these two black vectors. And again, that can be kind of read off from this kind of diagram. Okay, now notice once again, we've drawn the R sub alpha vector here. That's a common technique in diagrams. But in fact, all these vectors should be thought of as rooted at the origin, right? If you're talking about vector spaces, then really all the vectors are rooted at the origin. But for relative position vectors, we typically visualize them in the picture like this. Okay, now there are a couple of really remarkable results. And this is where we'll have opportunity to go through our summation notation, okay, as we crank out these results. So first of all, the angular momentum in any time, right, if there's one message to be taken away from chapter 10, when you talk about angular momentum, you must specify an origin. So let's model some good behavior here. Angular momentum, that's a term we use in the soccer leagues here, trying to model good behavior. Okay, set a good example. Angular momentum. Okay, about, see, we're going to specify the origin. And this is going to be our capital cursive O. Okay, so we've done due diligence. We're in the business of computing the angular momentum about that origin, okay? With that kind of clarity, we cannot go wrong, right? We'll simply write out the definition. Each particle contributes something we could write like this. Perhaps the clearest way is with parentheses. So we have the R alpha position vector. You know we must form a cross product with the momentum. That's the mass of the particle times the velocity vector. Okay, very nice formula. Then we plug in. All right, let's maybe emphasize that here with a nice colorful. We're going to plug that in. In fact, we're going to plug it in two places, right? The formula gets plugged in here. We'd like to express the angular momentum using these new primed vectors. Okay, so we'll take this formula, any occurrence of the R alpha vector, and here's one, we plug this in. And furthermore, we have this one here. Let's just really extend this arrow to make it clear. Yeah. We're pointing right at that R alpha. This one's the time derivative, so we must compute the time derivative of this thing. Okay, so when you do that, there's some effort here. We're going to skip some of the algebra. Let's just verbally describe the algebra. We're going to have a couple terms. In fact, we're going to have 4 terms, right? This first vector here, the R alpha vector, you see it's now 2 terms, the capital R and the R alpha prime. Here's this other vector. It too will be the sum of terms. You're going to have the capital R dot. That's the velocity of the center of mass. And then you have the R alpha prime dot. Okay, you see lots of decoration on the little r. Okay, so 2 terms here, cross product, 2 terms here. Obviously, we're going to use the distributive law for the cross product. We expand it. And there's a crucial thing here. The crucial thing is that the mass weighted sum of the primed vectors is 0. Okay, let's take a second to appreciate this. The sum on alpha and it must be mass weighted. So that means you take a scalar multiple here, this m sub alpha of the mass, times the primed position. Let's think about this for a second. You have all of these position vectors relative to the center of mass. If you multiply them by the appropriate mass of that particle and sum it up, you're going to get 0. This is very important. It will serve us well on many occasions. And again, how would you prove it? Well, you would take this lower formula, you would plug it in right here. Okay, so that R alpha prime, it's this minus that. So you have 2 terms to worry about. The first one is the sum of the mass alpha times the position vector, R alpha. Okay, well, let's remind ourselves that's capital M times capital R. The second term with a minus sign is the capital R. That's a sum, that's a constant in terms of this sum. It's independent of alpha, so you pull it out. What remains is just the sum on the masses. Well, that's the total mass. So you have a perfect cancellation. I just did a verbal description, but you can write it out and see that this is very nice. It adds up to 0. Well, if it's 0, then it's going to continue to be 0 if you differentiate it. So you apply the DDT operator, the time differentiation operator. And so the same statement is true for the mass-weighted sum of velocities of the relative position vectors. So in other words, this is 0. You can also put a dot right here. It's still 0. So that's very nice. We get some nice cancellation. And then what we have here, we'll just verbally use that discussion of the calculation. And here's the upshot. We have, first of all, a term from the center. This has to do with the center of mass motion, right? That's the position of the center of mass. That's the velocity of the center of mass. This is the contribution to the total angular momentum coming from the center of mass motion, obviously capital M. We got a couple of zeros. I'll just simply write plus 0, plus 0. Those are a couple of terms that vanish. You should go through this and write it out. They vanish because this is 0. So those are 0. And finally, a very welcome sight emerges here. We're summing over particles. What we have here is the mass of the particle, very, very similar structure, right? The R alpha prime, the position vector, cross R alpha prime dot. Okay, so this is pretty cool, right? That's a lowercase r with 4 pieces of decoration. We have the alpha, we have the prime, we have the arrow, we have the dot. The alpha is the particle label. The arrow means we got a vector. The prime means it's relative to the center of mass. The dot means we're looking at the time derivative. Okay, we're going to go beyond. We're going to have 5 pieces of decoration in a moment. Okay, so this has a structure of the center of mass. We'll write it like this. LCM plus L. It's going to be a big subscript. Motion about the center of mass. Okay, so the terminology that is often used here, this is the angular momentum of the center of mass, thought of as a point particle, right? That's the formula for a point particle. And this is the angular momentum of the motion of the system about the center of mass. So if you place an origin at the center of mass, then these are your position and velocity vectors. So we have this nice decomposition, and it came about from the distributive law. We had a cross product, we had some terms, we had actually at one point there were 4 terms, lots of terms. We argued that 2 of the terms add up to 0. And what remains is this nice structure, the center of mass motion and the motion relative to the center of mass. So in quantum mechanics, you know, you often talk about the spin-orbit interaction, right? There's orbital angular momentum. We could talk about the Earth orbiting the sun, right? If you think of the Earth as a point particle going around the sun, this would be the angular momentum of the center of mass of the Earth going around the sun. Furthermore, the Earth spins on its axis. And so there's angular momentum here, this motion about the center of mass. You have this extended rigid object. All the molecules in the Earth are rotating about an axis. And so again, spin-orbit decomposition. So that's our first interesting look at this kind of decomposition. Okay, we'll do something very similar for the kinetic energy. Okay, so there was the angular momentum about the origin. Let's do a similar calculation for the kinetic energy. Okay, and so I'll just write the title here, then we'll move the paper. So we got the total kinetic energy. And we're going to see a very similar structure. There will be some nice cancellation. Some terms will cancel out. And what remains then is something, this is something we said before, the capital variable. See how we have the center of mass motion depending only on capital R and capital R dot. And then this motion about the center of mass. Here you have just the lowercase r prime, the relative position vectors relative to the center of mass. Okay, let's go through the calculation for the kinetic energy. We'll start, as we always do. I want to write this formula. You'll see the similarity. There it was capital L for the total angular momentum about the origin. Here it's capital T for the kinetic energy. Okay, there's the formula, and you see the similarity in the structure. Here, you see we have the R alpha dot, the vector, that's the velocity vector dotted into itself. When we write this the exponent 2, that means we take this vector and we dot it into itself. Earlier, it was the R vector crossed into the velocity. So that's a slight difference, right? But now again, let's just emphasize, this is the kinetic energy in the inertial frame. So in inertial, remember that original origin, the cursive O, the cursive capital O. Okay, we're computing the kinetic energy in that frame. All right, let's get right to work. We're going to have a very similar calculation. Okay, we plug in that decomposition, right? So this thing here, the R alpha vector, is nothing more than capital R dot plus the R alpha prime vector dot. Okay, I'll put parentheses around it. That's what goes here. You have to square it, and again, that means you dot it into itself. Okay, so then again, there's some algebra. We're going to skip the algebra. A nice cancellation because of the vanishing of a certain mass-weighted sum. What we get the first term again, the capital variables. The kinetic energy of the center of mass thought of as a point particle. Okay, if all the mass were collapsed to a point, this is precisely what you would write. Then there's a 0. We have a certain cross term that cancels. I'll just write the 0 to remind us there was a cross term that canceled out. And then we've got our sum. And here it is, the moment we've been waiting for. It's a lowercase r with 5 pieces of decoration. This is almost unheard of. Here we go. It's r alpha. There's a vector because it's a vector. So there's our symbol for vector. Prime because it's relative to the center of mass. Dot because we have 1 order of time differentiation. And then there's the exponent 2. Okay, this is great. It's like a 5-star general with all these amazing pieces of decoration. 1, 2, 3, 4, 5. Okay, so that's pretty cool notation. The decomposition, once again, what you would say is TCM. We use capital T for the kinetic energy. This is the kinetic energy of the center of mass, and this is the kinetic energy of the motion relative to the center of mass. So again, motion relative to okay, so that's a big subscript, but it's worth it. We have to be very descriptive and clear. We have the kinetic energy of the center of mass and the kinetic energy about the center of mass. Okay, nice decomposition. Okay, so that's been quite general. Now we're gonna focus on a special case when you have all these particles, and we're gonna use the words rigid body, meaning there are interparticle forces that enforce a certain constancy. Think of a crystal lattice, and you have these various geometrical parameters having to do with the crystal lattice. Those are enforced by very stiff springs, so to speak. And in the limit of infinite stiffness, you have a rigid object. So we're going to be very interested in the motion of rigid objects. In the history of classical mechanics, these are called rigid bodies. So that's the standard term. We're talking about rigid body motion. Okay. So we have a collection of particles. Again, we'll treat this as a collection of particles, but we will assume the interparticle distances are constant. Okay, so the crucial thing here, again, collection of particles. Interparticle distances, lots of different interparticle distances. This is a kind of a nice, simple way to describe it. Really, for something like carbon monoxide, or let's talk about carbon dioxide. If you have a linear molecule with 3 molecules, if it's linear, then to say that the interparticle distances are constant is not sufficient. We also have to say something about the angles. And I'll put here parenthetically angles. Of course, you need 3 particles if you want to start talking about these angular parameters. But this is a pretty standard notion of rigidity. Okay, here's where we start to get into some very fascinating and some of it counterintuitive. There's some counterintuitive behavior. And I think you've seen this in your first year physics course. If you have, for example, a spinning bicycle wheel, if you remove a wheel from a bicycle, typically the front wheel, and hold the 2 ends of the axle and get this thing spinning, then as you try to move the wheel, it's very reminiscent of magnetic fields, right? There appears to be something going on that's kind of perpendicular to any effort you make. And so we're going to be studying gyroscopes, things like that, forces and torques. So we're going to be investigating the relationship between angular momentum and angular velocity. So the symbols on the left and right here are very familiar to us. The capital L, that's our angular momentum. We're going to be interested in the angular momentum of the rigid body about its center of mass. Okay. Omega, we're very familiar with this omega vector, right? The angular velocity vector. It tells you about the instantaneous axis of rotation, We're going to be solving problems now where this omega is not constant. It's going to be fascinating stuff. We'll include things like the, if you've ever been to a rodeo, and I certainly remember opportunities where we actually met a professional rodeo rider, a lot of skills, obviously. And so some of the tricks that can be done with the lariat, okay, amazing stuff, what they can do with the lariat. And you can talk about the angular momentum, angular velocity. In general, these two vectors are not parallel. Okay, typically in first year physics courses, you talk about cases where the angular momentum vector is parallel to the angular velocity vector. And now I realize I should have brought one of my kids' fidget spinners, because that would have been really cool. But let's imagine this thing is spinning about a vertical axis. I wonder if I could help to enforce that like this. Yeah, that's pretty good, right? Okay. So if you have an object with sufficient symmetry, if it's spinning about a vertical axis like this, I'm indicating with a pen cap, vertical axis, then yes, there are often cases where the angular momentum vector is parallel to the angular velocity vector. But we're going to see that in general, they are not parallel. Okay, the angular momentum vector could point vaguely in the similar direction, but it could be off by quite an angle. And this object here, it looks like a vector, but there's a double-headed arrow. This thing is a 3 by 3 matrix. Okay, 3 by 3 matrix. Okay. Furthermore, it is a second rank tensor. So both of these are true statements. It is a 3 by 3 matrix. But we want to especially focus on the fact that it's a second rank tensor. We can do this by using some colorful red ink. Second rank tensor. It's second rank, that's why there are 2 arrowheads, okay? These things are first rank. The omega vector, that's a first rank tensor. There's 1 arrowhead. The angular momentum is a first rank tensor. That's 1 arrowhead. We'll talk more about this. You have 1 arrowhead for every free index. So, you know, when you exhibit the components, you have the omega 1, omega 2, omega 3. And here you have L1, L2, L3. This is a matrix, so you require 2 indices. That's why it's second rank. So that's this object here. Okay. The other 2 objects, we're going to treat them as column vectors, and those are rank 1 tensors. Okay, so let's set this up, and we're going to arrive at this equation. This, of course, takes us to page 380. All right, page 380, wonderful page. That's our goal. As you know, the midterm number 2 covers up to page 380. And also, for one of the homework problems on the current homework assignment, part of the problem requires knowledge of this equation. And again, page 380, that's the crucial thing. All right, so what are we going to do? Well, we've already seen the structure of these calculations. We're going to look at the angular momentum. Okay. And notice this is the angular momentum about the origin. The origin need not be at the center of mass. Okay, we're doing a very general discussion here. And we will consider cases where you have an axis of rotation, you're rotating a rigid object, and the center of mass may be somewhere else. That's completely acceptable. So this calculation is completely valid. What we're going to do now is use the useful relation. Remember, we love this formula, the useful relation. If it's a rigid object and there's some instantaneous axis of rotation, then we can tell you something, we can say something about the velocity vector. All right, so here's what we get. right? The useful relation really comes through for us here. And then we are rewarded with a double cross product. I should say, it's properly speaking a vector triple product because there are three factors. I called it a double because there are two cross product operations. And without further ado, it's R alpha crossed. What's the velocity of that little particle? Well, it's omega cross R alpha. This is why we took a lot of time to really belabor this point. We went into it in detail. If you have a rigid object, if you know the instantaneous axis of rotation and you know the rate of rotation, this omega vector, yep, there you have it. It's assumed that this axis of rotation goes through the origin, then this is valid. Okay, so this is a very welcome sight, right? We really enjoy working with these vector triple products and the so-called back cab rule. The back cab rule, as you know, it's one of our most celebrated results. We got the document camera on a tripod. We mustn't bump it. Okay. We got the back cab rule. Back cab rule. If you have a vector triple product, no problem. You can remove any reference to the cross product operation. That's kind of a nice thing here. Two occurrences of the cross product, and the result involves only dot products, right? There's A dot C and A dot B. Those are dot products producing a scalar number. And then you have multiplication, a scalar number times a vector times scalar. And then there's a subtraction. Okay, so that's the nature of the game. We're going to invoke the back cab rule. Okay, we're going to carefully slide the book out of there. And we're back here to our calculation. Okay, so there's a little bit of effort, and let's talk about what we must do here. The first order of business, again, this can be conveyed very nicely using our notions of dot product. Then it's going to get a little bit messier. So we're summing over all the particles. We got the mass. There's the m sub alpha. Now what happens here, we've got the omega vector, and we got the r squared. Okay, again, that's, and now I should really put the R alpha. Okay, so far so good. And minus the R alpha vector. Let's fix that in the notes as well. And now there's a dot product. We got this R alpha vector. Yep, there it is, dotted into omega. Okay, so there you have it. What we have done here is implemented the back cab rule. There's one term here which points in the omega direction, right? We certainly welcome that, right? Because many people like to think of the angular momentum kind of pointing vaguely in the same direction as the omega vector. Well, here's a positive number multiplying omega. That's extremely good news, right? And mass, that's positive. R squared, or alpha squared, that's positive. Really welcome. Now this thing here, this is more complicated. It need not point in the omega direction. This is the position of some particle. It could point in any direction. And then we have a scalar multiple, right? This multiple could be positive or negative. Okay, so that's kind of the interesting structure that's emerging here. So what we're going to need to do here is write this out explicitly. Okay, to appreciate the structure. And our goal is to understand this matrix. This calculation that we're doing here, it might not be obvious, but this result is going to take the structure of a 3x3 matrix multiplying the omega vector, the standard notion of a matrix times a vector. Okay, and you can see that it is very much to be expected, okay? Because this operation here, notice this is linear, the key word linear. This is linear in omega. If you write omega as a sum of two other vectors, you could plug that in here and you would get two contributions again, one from the first contribution, one from the second. So this is linear in omega, and therefore it is to be expected that we have this. This is the most general linear relationship. The angular momentum is related to the angular velocity by matrix multiplication. That's the most general linear relationship. Special cases, for example, if you have a spherical mass distribution, then the angular momentum will be exactly in the same direction as omega. So for cases with high symmetry, like spheres and cubes, etc., centered at the origin, then you have a more simpler relationship. The angular momentum is just a scalar multiple times the angular velocity vector. But for an arbitrary object, so for example, if I take this thing and go like so, there's an arbitrary object without any special symmetry. And if you spin this about some axis, the angular momentum will in general not point in the same direction as the angular velocity vector. Okay, so that's going to emerge here. Let's see the kind of terms that emerge. Okay, let's be very careful. I'm going to scoot over. We're going to need some space. So we're continuing this calculation here. Okay, we're summing over the particles, alpha. We got the mass of that little particle, m sub alpha. Okay, and now let's, I really should do this as a really big parenthesis. Let's do it like that. We're going to write out the three components. We're going to explicitly exhibit the three components of the vector, right? This thing in square brackets is ultimately a vector with three components, an x component, and a y component, and a z component. And to really understand the distinction with those components, let's systematically work through this and appreciate where is the x component coming from, where's the y component coming from, and where's the z component coming from. Okay, so begin with the x component. That means we look at the x component of this vector. Well, that's omega sub x, right? And this is a scalar multiple, so we must copy over the same scalar multiple, right? R alpha squared is just some positive number. It could be 0, but it's a scalar multiple. Okay, now what's the x component of this? Well, the quantity in the parentheses there, again, that's a scalar. And here's the vector. So when we ask about the x component, we must use the x component of this vector, and that's just x sub alpha, right? Remember our general agreement, the r vector has components x, y, and z. So r sub alpha vector has the x component x alpha. Then we simply copy over the parentheses. All right, and what can we say? Well, we must now write out this dot product. So that's going to be our x alpha times omega x plus y alpha omega y plus z alpha omega z. Yeah, I got a little cramp there, but we got it. Okay, that's the x component. Now there's a comma here, and this comma should be every bit as bold as this parenthesis because we're exhibiting the three components of this vector. All right, let's go for the y component. So it's the y component of that. Again, that's omega y, same scalar multiple, the r alpha squared, minus the y component of that, that's y alpha. And now it's the same thing. I'm going to put ditto because you simply copy all that stuff over here, comma. Okay, let's look at the z component. And we're looking at omega z. That's the z component of that vector. We'll multiply by that same scalar, that's the r alpha squared, minus the z component of that vector, times the scalar, and it's the same scalar, we'll just put ditto. Okay, and then we'll close the big parentheses without running into the little comma. Okay, so yeah, the point of this discussion is we're taking a very careful look at this angular momentum vector, and we have written it out. So having done that, we see the structure that emerges, right? And it is this structure here, this celebrated formula that the angular momentum is a matrix times the angular velocity. That's what's emerging here. So what does that mean? Well, let's write this out. We'll use the usual conventions for matrix multiplication, okay? this very compact statement, right? The angular momentum vector is equal to a 3x3 matrix times the angular velocity vector. Okay, and of course in physics 89, or perhaps you took math 54, this stuff is very central to the course. So this equation, written now in great detail, looks like this. Okay, the angular momentum vector, it's a 3-component vector, and we like to write vectors as column vectors. So there it is, Lx, Ly, Lz. This is equal to, well, there's a matrix, a capital I for inertia. Okay, and we'll use the international conventions. This is unfortunately something where everyone in the world agrees. There's really very nice international agreement. Though there is an arbitrary decision to be made, everyone agrees. The first index tells you how far down to go. The second index tells you how far over to go. So the first column here, Iyx, Izx, right? So you see that first index telling you how far down to go. The second index, how far to the right. Here's an Ixy, here's an Iyy, Izy. Okay, and the third column, Ixz, Iyz. You see the first index told us to come down here to the y row. The second index tells you to come over to the column z, the z column, the third column, Izz. Okay, that's the matrix. And here we have, this factor is a column vector, omega x, omega y, omega z. Okay. So this equation, again, is perfectly identical to that one. I think we should liven it up here with a nice, that equals, is that thing. It's also equal to this, absolutely true. Okay, and this thing here. Okay, so what have we done? We have written this in the very compact notation that you'll see on page 380. Now here's the important thing. In the textbook, they just use boldface, right? If you don't believe me, let's look at page 380. They'll just use boldface, and they don't have the clarity that we have here, writing it by hand with a double-headed arrow. You see that wonderful clarity that emerged. We've made it only too clear that that is a rank 2 tensor. In the book, okay, you see L equals I omega. We use boldface for vectors L and omega, fair enough. Boldface is also used for the inertia tensor. Okay, so here's an example. When we write that same equation by hand, we use a double-headed arrow because that is an object. It has two, every entry you see, it has two indices. Two indices, so you have a double-headed arrow. One index, you have a single-headed arrow. One index, single-headed arrow. Okay, so now you see what happens if we can read off these coefficients because the structure is there. You know from the rules of matrix multiplication, let's work out one of these. The rules of matrix multiplication tell you that you take a row in the matrix. So for example, here's a row. Okay, you take the row, that's the first row in the matrix. You form the dot product with this column vector here. That gives you Lx. Okay, so you see Lx is equal to, this is per definition, right? This is coming from the very definition of matrix multiplication. We got this first coefficient, Ixx, omega x. We got the second coefficient, omega y. We got the third coefficient, right? So matrix multiplication is very important to us. And this equation here is just a reiteration of what's coming to us from the definition of matrix multiplication. But now we can make a direct comparison with this one here. The first entry here, right? Remember, we have the commas. Let's see, I should point like this. There's a comma there. There's a comma there. This thing here, together with that m and the summation, this is the first component. This is L sub x, all right? So this is equal to, let's copy over what we learned over here. This is equal to the sum on alpha. And now I'm copying over the first component of this vector, which we worked out in great detail. There's the m alpha, and then you got the omega x, the r alpha squared, minus x alpha times this thing in parentheses. We got to copy it over. It's x alpha omega x plus y alpha omega y plus, there's the z alpha omega z. Okay. Now, I think for clarity, I'll kind of put a dividing line in here like so. Okay, that is, this appears to be a messy expression, right? Does it not appear to be a messy expression? But let's appreciate that every term is proportional to one of the components of omega. There's omega x. There's omega x again. There's omega y, and there's omega z. So you see the structure, which is shown here in this line, in the just one line of equations above. Whatever you have multiplying omega x, we're going to call that I sub xx. And you can read it off, right? There's a contribution here. Here's an occurrence of omega x. And so we have the sum on alpha, m sub alpha times r sub alpha squared. But not only that, here's another occurrence of omega x, and there's a minus sign and an x alpha squared. Okay, so in this way, you see we've achieved a major goal. We have, by using the back cab rule, we've succeeded in showing that the angular momentum vector is a matrix times the angular velocity vector. The crucial thing is that inside of this matrix, there are no occurrences of omegas. The matrix depends purely on the mass distribution. So you'll see formulas that have the masses of the little particles and their positions. The matrix is an attribute of the mass distribution. Okay, and let's appreciate that there's a hierarchy here. Okay, there's a very important hierarchy. Earlier today, we talked about the capital M. This is an attribute of the mass distribution. It's called the total mass. This one depends only on the little masses. It doesn't care about the positions. Here's capital R. This is also an attribute of the mass distribution. And this is nice to see how it depends on both the masses and the positions. And very much in the same footing now, we'll put our moment of inertia tensor. Okay? What we've seen is this too is an attribute of the mass distribution. And you see it's part of a hierarchy of tensors. You can certainly construct rank 3 tensor, rank 4 tensors, etc. And I think I mentioned there was a very fascinating, actually there have been several missions where they put orbits, satellites orbiting the moon, and they measure these and higher. They go up into the thousands, very high rank tensors for the mass distribution inside the moon. Okay, so what we've seen here at this point is that we have this structure and we have these formulas for the very components here of the matrix. The quintessential, we'll write this down as our closing remark. This Ixx, you see we can read it off now. Ixx is a sum. We must sum over the mass distribution. And you see the structure that came out was the R alpha squared minus X alpha squared. And of course, this can be simplified. It's just the Y squared plus the Z squared. So that's one important revelation. That's the structure of all the diagonal elements. The off-diagonal elements are going to look like this. There's a minus sign coming from this minus sign. And we got this sum. We're summing over the mass distribution, M alpha, X alpha, Y alpha. So this is the fundamental structure that has emerged here. The XZ, very similar story. You put the X and the Z here, the YZ, etc. And for the diagonal terms, they all take this form here. Okay, so that brings us to the conclusion of today's lecture. What I'm going to do here is stop the recording, and then I'll stay here for questions. Oops. Now I hit the wrong button, but I can cancel out of this. I'm trying to stop the recording. Stop.